So next, what we should talk about is the following proposition, and it says that if a function f, which I'm going to write is the real part plus the imaginary part, is holomorphic on G. So if f is holomorphic on G, then U and V are harmonic. Okay, so there's one piece of the connection between holomorphic functions and harmonic functions. So then U and V are harmonic on G. Remember that harmonic on G, I don't know if I said this in the previous video, but when I say on G, what I mean is that these are really functions of two variables, and we want this equation to be true for all values x and y in G. So that's what it means to be harmonic on G. So maybe this equation isn't true elsewhere. Maybe the second derivatives are piecewise defined, whatever. But if it's true for all values on G, then we say that U is harmonic on V, and likewise for V. So the proof is straightforward. The proof is much better organized in the book, but I just want to just talk about the main ideas, and this is like 95% of the proof anyways. The Cauchy-Riemann equations tell you that, so the Cauchy-Riemann equations, just as a reminder, are that if f is u plus iv, then the partial of u with respect to x is equal to the partial derivative of v with respect to y, and the partial of u with respect to y is equal to minus the partial of v with respect to x. Okay, so these are the Cauchy-Riemann equations. This is a nice, neat criteria for determining whether or not a function is holomorphic over a certain set. And so what we're going to do with this is I'm going to take and I'm going to look at the second partial of u with respect to x. And notice that that's just the partial of v with respect to y taken with respect to x, because I'm thinking of taking the partial of u with respect to x and then taking the partial with respect to x again. But u sub x and v sub y are equal by the Cauchy-Riemann equations. And so that's going to be equal to v sub y x. Now v sub yx, we're going to compute again by noticing that if I take the second equation, and if we differentiate both sides with respect to y, or let me organize it just a little bit differently. Let's take u sub y and differentiate that with respect to y, and that's going to be minus v sub x with partial of that with respect to y, so that's minus v sub xy. Now, if v is such that it has continuous second partial derivatives, then the mixed second partials commute, meaning that under the hypotheses, v sub xy equals v sub yx. And therefore, if we add all parts of this equation on the left side, we'll get the second partials with respect to x plus the second partial with respect to y. On the right side, we're going to get this term, v sub yx, minus v sub xy. But if they're equal, then subtracting them gives 0. Okay, so not very well organized as a proof, but this is the idea. That's what I wanted to convey for this proposition. Okay, so again, the proposition says that if a function's holomorphic, then the real part and the imaginary part are harmonic. Okay, on the same set of holomorphicity. On the flip side of that, okay, so on the flip side of that, if, so this is another proposition. And this is kind of the reverse side of the coin. If U is harmonic on G, on a set G, then there exists a function, so there exists a harmonic function V. Again, this is harmonic on G, so that F, which is U plus IV, is holomorphic on G. Okay, so what this says is it's kind of the flip side of the coin. The first proposition says if you start with a holomorphic function, then the real and the imaginary parts are harmonic. What this proposition says is that if you start with the harmonic function, you can find another function v so that u plus iv is holomorphic. So in a certain sense, harmonic and holomorphic are describing the same kind of phenomenon. It's two different ways to get at what it means for this function to be differentiable on this whole open set G. So what I want to do is, rather than prove this proposition in general, is I want to explain how you would find V from a practical perspective. So the book goes through and details exactly how you can come up with V in every situation. I find it a little bit prescriptive. So what I want to do is instead just explain this through example. I would still encourage you, as you're going through and reading the book, which is part of your assignments, I would still encourage you to go through and read that proof and see that you can construct this function V for all harmonic functions U. But what I want to do is let's start with the function U of xy is x squared minus y squared. This is our first example that we talked about. In fact, it's the only example that we've talked about. We showed that U is harmonic on the entire complex plane. And what we're going to do is we're going to look at, we're going to try and find V. Okay, so that V is harmonic and that U plus IV is holomorphic. And so here's how we're gonna do this. First, we're gonna look at we're gonna basically kind of exploit the Cauchy-Riemann equations. So we want to find a function V so that V sub xx plus V sub yy is 0. This is a V. And so that U sub x equals minus V sub y, and U sub x equals V sub y, and U sub y is minus V sub x. That's what we want. Okay. So what we're going to do is we're going to start here. Okay. And we're going to notice that if I take U and if I partially differentiate with respect to x, then in this case, what's going to happen is we're going to get 2x. And this is supposed to be equal to the partial of V with respect to y. And so if you integrate both sides with respect to y, this is kind of undoing the partial derivative. This should give you V. And so this tells you that V is going to be equal to 2xy plus a constant with respect to y, which is some function g of x. Okay, so this does not determine what this function g of x is. But what you can do then is you can take the partial derivative of V with respect to x. So if we take this term now and differentiate just with respect to x, what we're going to get is 2 sub y plus some g prime of x. And recall that we want V sub x to satisfy this equation. Okay, so here we need to notice that U sub y is equal to minus 2y. And so if we compare U sub y and minus V sub x, let me just write it a little bit nicely. Since we want U sub y, which is negative 2y, to be equal to negative V sub x, this implies that g prime of x is 0, so that g of x is really just a constant. Okay, and therefore, if I go back to our expression for V, any constant function g of x will give us a harmonic conjugate V. Okay, and so therefore V of xy can be 2xy plus any constant. Okay, however you want to write that. It's 2xy plus some constant, if you want to call it some constant z naught. Okay, anything there will work. Now, what's the function? So now I just want you to notice one more thing. So just notice that kind of by construction, if I look at f, which is u plus iv, this is x squared minus y squared plus I times 2xy plus z naught. This is going to, by definition, satisfy the Cauchy-Riemann equations because that's how we came up with V. But also V happens to be harmonic. So we can verify that V is harmonic. Of course, if V is 2xy plus z naught, what we're going to get is, let's see, If we differentiate this with respect to x, we're going to end up with 2y. So v sub x is going to be 2y. And that tells you that the second partial with respect to x is 0. And likewise, the partial with respect to y is 2x. So the second partial with respect to y is also going to be 0. And so, of course, when we add them up, we get 0. So v is harmonic. But notice that f is holomorphic because it satisfies the Cauchy-Riemann equations almost by definition of how we constructed v. And I also just want to point out, just in case it's not obvious, this is really the function, if you think about it, f of xy, or f of z, if you like, is really just the function z squared plus some constant, I times z naught. Okay, and we know, of course, that z squared is holomorphic everywhere. We know how to calculate its derivative. We know basically everything about z squared that we need to for now. But this is just an example. It turns out that you can do this process for any harmonic function u, and you can kind of come up with, derive a function v so that u plus iv is holomorphic. Okay, so that's the two sides of the same coin here. Holomorphic functions and harmonic functions, in a certain sense, are describing the same phenomenon.